Hi students, today we are moving to another important topics with the chemical kinetics. I will discuss consecutive reactions, reversible reactions, and the last part of video dedicated to solve two questions from parallel reactions. If you look at the syllabus, consecutive and reversible reactions, syllabus says only mention only. Therefore, the detailed mechanism, its derivation are not the scope of our BSc syllabus. You can learn it when you do physical chemistry in MSc classroom. Okay, let us introduce here what is consecutive reactions. This is a special kind of reactions that's happening around us, particularly in nuclear reactions. This is a symbolic representation of consecutive reaction. Initially you have reactant A only. That A is converted into B, B is converted into C. Here you have to clarify one idea. The conversion of B to C doesn't take place after all B is formed. The conversion of B to C is a simultaneous process when A to B conversion happens. Therefore, B has a role of intermediate here. Once the reaction is over, you will get more C, not equal amount of B and C. That kind of reaction is called a consecutive reaction. One example, uranium is converted to neptunium in 23.5 minutes. Then neptunium is converted to plutonium. Okay, this is a one kind of consecutive reactions. Therefore, this type of reactions, he has required a different kind of treatment for measuring the rate of reactions, because they are not usual reactions which I have already discussed in our chemical kinetics. Therefore, scientists have introduced a different methodology to determine what is the concentration of B, what is the concentration of C, and what is the concentration of A in different time intervals. And this is a graphical representation of consecutive reaction ABC. And initially you have A only because it is a reactants you have taken. B is not the reactant you are taking. You see, initially B is formed a lot. B is formed a lot. And at a particular time, concentration of B is maximum. Then B is decreased almost to 0. You know why? That B has been converted to C. This is the concentration of C. The initial time period, which is small, B is small. But after a given time period, C has piled up, or the concentration of C has increased a lot. Okay? Correspondingly, B decreased. At a particular time, you look at this point where rate of formation of B is equal to rate of formation of C. Yes, that is called a steady state approximation. The steady state approximation, if an intermediate is formed, at that intermediate, the rate of formation of that intermediate is equal to rate of consumption of that intermediate. Fine. We have already discussed it. Anyway, the rate of formation of products is equal to K2 into B. You know why? C is formed only from B. Not a molecule converted to C directly. Therefore, rate of formation of C is equal to K2 into B. But we don't know what is the concentration of B, because B is not a molecule we are adding to as a reactant. Therefore, we are applying a steady state approximation here. What is the steady state approximation says? What is the steady state approximation says? During a reaction, if an intermediate is formed, the rate of formation and rate of consumption of that intermediate will be 0. What is the rate of formation of B? That is K1B. K1B. Because this is the step where B is formed. What is the rate of consumption of B? K2B. Because that is the step where B is consumed. Therefore, K1AB minus K2B is equal to 0. That is steady state approximation. From there, you will get the concentration of B. B is equal to K1A divided by K2. Okay. Now, you apply this B is here. Therefore, dC by dt is equal to K1 K2 divided by K2. Instead of B, you are writing A. That is nothing but the K1A. Therefore, dC by dt you got in a first order equation. In the first order kinetics, I have derived an equation. We have already learned A is equal to A0 into e raised to minus KT. K1 KT. Here, right, constant K1. Therefore, dC by dt is equal to K1 into, instead of A, you can write A0 e raised to minus K1t. Okay? Or dC is equal to K1 A0 e raised to minus K1t dt. If you integrate dC is equal to K1 A0 e raised integrate K1t dt, because A0 and K1 are constant. Therefore, concentration of C, integration product of this is C, is equal to K1 A0 integral product of e raised to minus Kt dt, K1t. I stop here. We can go the details, but that is not scope of our syllabus. Okay. Now I go to another reaction that is called the reversible reaction. Reversible reaction. What is reversible reaction? This is another kind of reaction normally happens in chemical kinetics. That is K forward and K backward. Reversible reaction, it is a very slow reaction. And there is an equilibrium. There is equilibrium. And there is, at equilibrium, rate of forward is equal to rate of backward. And delta G is very small, almost equal to 0. If it is equilibrium, delta G is equal to 0. Therefore, reversible reaction is a reaction which takes place in backward direction and forward direction. And reversible reaction attain an equilibrium when rate of forward is equal to rate of backward. Therefore, this type of reaction also requires a special kind of treatment for their chemical kinetics. How can we do that? It is also a lengthy derivation. We are not going to derive that topics in detail because that is not our scope of syllabus. Anyway, time and concentration. Suppose A, concentration of A, concentration of B. This is forward and this is backward. This is concentration of B and this is a constant. And this point is called equilibrium. If straight line point is called equilibrium. Okay. How can we derive a chemical kinetics here? Write equation for this. Okay. You see, this is our reaction A equilibrium B. Initially t is equal to 0, only a 0. Okay. T is equal to t, a minus x. This a minus x can be called a. This x is called to b. At equilibrium, a minus xe and xe. Okay. Now rate of forward reaction is equal to kf into A. Concentration of A, that is kf into A minus x. Rate of backward reaction is equal to Kb into B, that is Kb into x. Now what is the net rate of reaction at a given time? Net rate of reaction is Rf minus Rb. Rf minus Rb. That is dA by dt minus dA by dt is equal to Rf minus Rb. What is dA? I can write dA is equal to minus d into ax by dt is equal to Rf minus Rb. This dA is minus dA by dt, that is a constant. Therefore, dx by dt is equal to what is Rf? Kf a minus x minus kbx. This is the differential rate equation for equilibrium reaction. We can derive it, we can integrate it. You can learn in post graduation level. Okay, thank you for watching.